The same music system that was responsible for this, Half-Life, helped created something as beautiful as this. Or even... But why? Why do some notes go well together while some others don't? And that's what we're going to be investigating today. Why do some music notes sound good together? And hopefully before we start, you know a bit of music theory. Hopefully you know that in modern music there are 12 different notes, as you can see here, and each notes are what we call a semitone away from each other. Or in other words, if you go from a C to a C sharp, that's a semitone. You go from an E to an F, that's a semitone, and you kind of get the idea. And of course in music there's a lot more notes in this. There'll be notes that are higher than what you see here, and there'll be notes that are lower than what you see here. But they all will be represented using the same set of letters. And if you can see here, these two notes are both a C, but are separated by 12 semitones. They're basically the same notes, but in a different pitch. This C is higher than this C. These two notes are what we call octaves, because they're the same notes, but separated by 12 semitones. And what we're really kind of interested in are musical scales. For the purpose of this video, we're only going to be discussing the major scale. So for example, the C major scale will consist of a certain root note C and then 6 other notes, so 7 notes in total. Of course, these notes will repeat to the higher end and to the lower end of the piano. Just as long as they are those notes, they all belong in the same scale. Now say we want to look at the C sharp scale, all we have to do is move a note a semitone higher. So the root note C, if we move a semitone higher, we go to the C sharp, and the same with all the other notes. And this will still be a major scale, but just the C sharp major scale. And you can kind of do something similar for all the other scales as well. And notes that belong to the same scale will sound good with each other. So for example, this note here is a C. Now I play notes that belong to the C major scale, they'll all sound good with each other. Listen. See, they sound quite good together. And if I play notes that don't belong in the same scale, they would not sound good together. Have a listen. Something like that. But why? Why do those notes that belong to the C major scale sound good together while the other notes doesn't? At this point we'll step in to the maths and physics zone of this whole topic. But before we actually discuss the music and the notes, we have to discuss sound and sound waves. Because sound are basically just longitudinal waves, which means that the particle which are transmitting these sound waves are vibrating in the same direction as the actual direction that the sound is traveling in. Now the vibration of the particles causes the pressure of the air around that certain area the wave is being transmitted to change. So as the sound is being transmitted, the pressure of the air of a certain area will be compressed, then rarefied, then compressed, then rarefied, and this just keeps going on as long as the sound is being transmitted. So the particle would vibrate one way and then vibrate back the other, and however fast it takes for the particle to complete that vibration, that will be how long it takes for the air to be compressed, then rarefied. How often the particle vibrates back and forth is what we call the frequency. Frequency is how many times the particle vibrates per second, and it's measured in a unit called hertz. If a particle in a certain way vibrates back and forth 1 time a second, its frequency would be a hertz. If the particle is vibrating back and forth 1,000 times a second, then its frequency would be 1,000 hertz or a kilohertz. Now the more the particle vibrates per second, the faster the particle vibrates, the higher the frequency of the wave, which will lead to a higher pitched sound. And if you have a science lab with proper equipment, you can even try to find frequency of any sound. You can have some kind of speaker producing some sound, and on the other side you can have a machine that picks up the changes in pressure of the air around that region that's caused by the sound, and you can plot that pressure change against time, and you can use the graph produced there to find the frequency of whatever sound's coming out of the speaker. Now, a more compressed pressure time graph, like the one you see at the bottom here, shows that there are more compression and rarefaction happening per second, which means that this graph will represent a higher frequency sound. But let's go back to music. Let's look at the frequencies of the 12 music notes. Well, as you can see here, we start off at the middle C, and then we keep going up until we get to a C an octave higher. And as you can tell from the table, the higher the note is, the higher its frequency will be. Now, are there any patterns between the frequencies of each note as you go up a semitone? Well, if you try and find the difference between the frequency of a certain note and the frequency of a note a semitone lower, you don't really see a pattern just yet. Now, instead we take log base 2 of these frequencies and then find the difference between those numbers, we start to see something. We see that the difference of the log base 2 of the frequencies are all the same, and it equals to 1/12. And this means that the Western music notes are really all just going up in some sort of logarithmic scale, which is quite neat. And it's worth mentioning that notes that are an octave away from each other, like this C and this C, have got frequencies which are basically doubles. The frequency of this higher C is double the frequency of the middle C, and if you think about logs and stuff, you'll kind of see why. But why do some notes sound good together? We still haven't quite answered that question. Well, let's look at the frequencies of the notes that are in the C major scale. Can we see some sort of pattern between the frequencies of these notes? Well, not yet. Now, really, all these notes, because they're in the same scale, will sound good with each other. But for the purpose of discussion, let's take two notes which sound really, really good with each other. I'll discuss what we call perfect fifths. Now, perfect fifths consist of two notes, a certain root note and another note which are 7 semitones higher. So, for example, we take C as the root note, its perfect fifth would be a G, which is 7 semitones away from the C. Now, interestingly, if we look at a C major scale, we can see that the G is in fact the fifth note in that scale. Maybe that's why they call it a perfect fifth. I don't really know. If I take the C and I play it along with the G, it will sound good together. Have a listen. If I play the C with another note that we know won't sound good with the C, like an F sharp, which is this note, then this thing will sound horrible. Have a listen. So notes like C and G, which sounds good together, are said to be in consonance with each other, while notes that doesn't go well together, like C and F sharp, are said to be in dissonance. But still, like Liam Gallagher likes to ask, why? Sorry about that. Why are C and G in consonance with each other while C and F sharp are in dissonance with each other? Well, to see why, we have to look at the frequencies of these notes. So let's compare the frequencies of the C, the G, and the F sharp. Well, here's the numbers. Can you see some sort of pattern in the numbers? Not really, can you? Well, it's a bit hard to think about in terms of numbers, so let's visualize it using waveforms. So this is a wave representation for the note of C, for the sound wave for the note of C. Now, on the same axis, I'll either draw a wave for the G or the wave of the F sharp on it. Can you see something in the waves of C and G which you don't see in the waves of C and F sharp? Well, if you look carefully, you can kind of see that the waves of C and G are in a way synchronized with each other. Every time the wave of C completes 2 cycles, the wave for G completes 3 cycles. There's this sort of pattern. The waves are synchronized with each other, and this is what you can't find when you draw the waves of C and F sharp. And with the principle of superposition of waves, which allows us to add 2 waves together, if we add the waves of the C and G together, the wave that we create will have regular patterns, as you can see here. We try to add the waves of the C and F sharp, we see that we get no pattern. We just get some wiggly lines, which doesn't really have any repeated units or anything. And the fact that the waves have got some sort of pattern means that the 2 notes C and G will sound good with each other, because the sound waves are all going to be coming in a regular repeating pattern, hitting to your eardrum and then giving you a repeated constant vibration, and it just sounds good. And these constant patterns are what make music sound good in general. I mean, if you have a drum and I hit a regular beat, then the beat would sound good. But if I just hit something randomly and not follow any sort of beat, it wouldn't sound as good. Same with the sound waves. When they come in at a regular pattern, it would just sound better to your ears because it beats in your eardrums with a regular pattern. But how do these waves relate to the frequencies of the sound? How do the frequencies of the notes that sound good together relate to each other? Well, let's look again at the frequency of the C and the G. If you do a bit of math and stuff with it, you can see that the frequency of the C and the G can be reduced down to a simple ratio. The ratio between the frequency of the C and the frequency of the G could be reduced down to a simple ratio 2:3, which is kind of consistent with our waveforms, isn't it? Because every time the C completes 2 cycles, the G completes 3 cycles, and the ratio between C and G is 2:3, so it makes sense. And in fact, if you compare the frequency of the C with the frequency of the other notes in the C major scale, you can see that you can make some sort of ratio between frequency of the C and the frequency of the other notes. And you can even try to find these ratios in other major scales. Try to find the ratios between the frequency of the root note of that scale and all the other notes, and you find that you'll actually get the same ratios as you did when you try to find the ratio of the C major scale. It works for all of the major scales. Just don't talk about the minor scales just yet. And that's why the notes of a certain musical scale will sound good with each other, because there's some sort of ratio between the root note and the other notes in that scale. And this means that the waves of the notes in the scale will in a way be synchronized with each other, like how we saw earlier with the C and the G. But while the notes do sound good with each other, they don't sound perfect with each other. If you look carefully enough, the ratios are actually just approximate ratios. And there is a reason for this. The frequencies of the musical notes are set according to that logarithmic system that I've explained earlier in the video. And so with those set numbers of frequencies, the ratios between those frequencies would just be slightly off. If you adjust the frequencies of the notes so that the ratios are exact rather than being approximately correct, then you would upset that logarithmic system that the notes were set up at originally. And that's not a good thing, because if you change the frequencies of the notes in music, then you might upset the entire music system. And so we just kind of have to settle with these approximate ratios. But to be honest, we can't really tell the difference. We can't really tell that the tuning in music is not quite perfect, which means it's good enough. And yes, guys, this is the end to the video on why music sounds good, because the notes of a certain music scale will have waves which are synchronized with each other. And to be honest, this might be quite a tricky topic to understand. In explaining it, I tried so hard, and I've got so far. But in the end, it doesn't even matter. I had to fall to lose it all. But in the end, it doesn't even matter. Now you want to look a bit further into the patterns between the waves of two different notes and just have a little play around, see which two notes create some patterns. I've created a little file here on a website called Desmos. You can go check it out and just have a play around with it. It's not perfect, but it's quite good, I think.